Good afternoon, friends. Hope this finds you well. It's Ben again. This is a video for the vector calculus class. In theory, this is the last video for the vector calculus class. A couple of things to start off. One is the comment that this video may run kind of long because there's lots of little things to put together for it. But I think when you get to the actual assignment, that the assignment will be relatively short. So, yeah. The other thing to mention is I probably look a little goofy here because I am dressed with my sweater on and stuff. I'm feeling a little bit of a chill. So it's the second day after I took my first vaccination shot. So that may be what's going on with that. In any case, the thing that we're going to take a look at today, I'm kind of loading up as I go along here, is going to be talking about second order linear differential equations, specifically those where the coefficients of the y prime, and so forth are constant coefficients. And then we're going to talk about the possibility of having a homogeneous equation, which is to say the right-hand side, the stuff that doesn't have a y in it, if that's 0, we refer to it as a homogeneous equation. If it's non-zero, it's non-homogeneous. So the two different situations sort of build upon each other, but the whole approach to it is relatively organized. It's just an incremental thing where you build up stuff to get it to go, right? I'm going to share a screen here to show y'all the little presentation-y thing that I have prepared for this, and we'll see how that goes. All right. Looks like it's actually going to work with the sharing. Yay! So the thing we're talking about, again, second order, just means that you'll have a y double prime appearing in it. Linear means that the y prime, the y double prime, and the y they can be multiplied by functions of t, but not by each other. And there can't be any, sines or cosines or square roots, nothing but linear appearances of these three things. Now, then over here on this other side, that g of t, and for that matter, this p of t and q of t, could be anything. Those do not have to be linear at all. The linearity is really about the three iterates of y there. So then if in particular this portion over here, which is referred to as the driving function, if the driving function is the 0 function, not just if it intersects 0 somewhere, but if it is 0 for all values of t, we refer to the equation as being homogeneous. And I think I have occasionally misspelled it as homogeneous instead of homogeneous. One thing we run into there is that the word homogeneous or homogeneous are used in every field of math, and they always mean 2 or 3 different things. So in every field. So yeah, I will occasionally misspell it, sorry. And we are in particular going to be interested in working this out where these coefficients, the p and q, are constant. You can work it out in a more general sort of way. That's not true. You can work it out with specific examples when you've got a p and q that are non-constant and get it to work out. But it's hard to form a general theory. By dealing with the p and q as being constant, we can do something that's a local theory. Little beyond the scope of what we'll get into, but you can actually talk about the stability of your solutions and whether a numeric solution is going to end up being close enough or whether it will tend to, drift away over time and things like that. So we're going to look at a little bit of parallelism here. If you remember, for our separable differential equations, we'd have dy dt equals some p of ty, p of t times y. And it can be more complicated than that, but we're going to think about the linear ones. So that is going to mean that it has to be kind of along those lines. And when we did that, we would divide both sides and get these two integrals. And on the left-hand side, we would end up with a log y, and then you would exponentiate in order to get your final solution here. And so you ended up with your y being some constant times e to an integral p of t dt, all right? In particular, if instead of p of t, if you had a number over there, like say 2, then you'd end up with an e to the 2t, right? So that's kind of a motivation in what we're doing now. So if you looked at the linear setup for first order stuff, then you would have this y prime plus p of ty equals q of t. And you remember we did that whole thing with the, what do we call that? The integrating factor, mu, and you'd multiply both sides by it. And that integrating factor ended up being this e to the integral p of t dt. And then you would multiply both sides by it. You would have to integrate the q of t, but then this side would end up becoming just the mu times the y when you integrate it because of the product rule getting reversed. And this meant that our final solution we ended up with out of this was c times e to the integral p of t dt, and then some complicated term that would come out of the integration. However, what I want you to think about is if this had been 0, then when we integrated this, that yp wouldn't be there. That complicated term wouldn't be there. And I'm referring to that as y sub p for a parallel that's going to come up later, right? So if you've got a homogeneous first order linear differential equation, then the solution to the homogeneous equation is going to be c times e to something that came from an integral. As a matter of fact, the first exposure I had to differential equations before I took it, a more senior student made this comment to me, the answer is always e to the something. And he actually advocated that if you don't know the answer, write e to the something and hope for partial credit. Seems a little goofy in retrospect, but it does sort of fit what we're seeing. It's always e to the something that you integrated. So here we're going to look at a homogeneous linear differential equation with constant coefficients. Specifically, we've got constant coefficients. And it will always have this form here. The ay double prime plus by prime plus cy equals 0. And if you just make that guess that you think y is going to be e to the rt, then the y prime would have to be r e to the rt, and the y double prime would have to be r squared e to the rt. So if you plug those in here, you will end up with an a r squared e to the rt, a b r e to the rt, and a c e to the rt. And of course, e to the rt can be factored out of those, and e to the rt is never 0. That means you can divide it out. If there was a possibility it could be 0, you shouldn't divide it out. You should look at that possibility for it to be 0. So that's something a lot of times people miss. But that implies that this quadratic equation, whatever the solution to it is for the r values, that is going to give you a solution, e to the rt. Now, of course, remember when we looked at this sort of thing before, we got that c in there. So if you end up getting two solutions, you're going to refer to one of them with a C1 e to the R1t, and then the second one as a C2 e to the R2t, okay? And so you'll just go ahead and add those together and have all the possible solutions. What we discover is that the order of the differential equation decides how many degrees of freedom that you have, or how many, if you don't mind the phrasing, what the dimension is of your solution space, right? Kind of like the dimensions that we thought about with the parameters when we parameterize something. If you only had one parameter, it was one dimensional like a curve, two parameters, two dimensional like a surface. So in any case here, then we have the possibilities when you write a quadratic equation that either you have one real solution with a repeated root, or you have two real solutions where the roots are distinct, or you have two complex conjugate solutions. Those are the three possibilities for a second order equation, second degree equation. You ought to look at this and have a little bit of an epiphany, though. It wasn't really particularly special that we stopped at second degree. You could have had a third degree equation, and that would give you a cubic equation to solve. Fourth degree, quartic, quintic, you know. Unfortunately, once you get up past fourth degree, you don't have a lot of hope of solving them unless things just work out perfect, you know. But in any case, I want you all to catch that these indicial equations that you write are the main thing to solving these. And then you have the three cases of having one or two real solutions and then two complex conjugate solutions. So if you have two real distinct solutions, then your general solution is going to be C1 e to the R1t plus C2 e to the R2t, okay? And in general, what's going to happen with these, let's say we're, instead of in general, let's look here at this one here. You immediately write down an r squared, a minus 2r, and a minus 8, and set it equal to 0 and solve. The solutions you'll end up with are positive 4 and negative 2. So if we were to draw a solution here that was something along the lines of an e to the 4t, because the other piece of it is going to vanish, is going to go to 0 as t goes to infinity, then all of your solutions are going to go in towards some coefficient times e to the 4t, all right? I'm not going to hop over to Desmos and try to graph it because that'll make things super long. In any case, you don't have to always have one positive and one negative. I just made that happen in this particular example. But it can be anything where they're distinct and your solution is just going to look kind of like that. If it's an initial value problem, then you'll have to, you'll have to plug in the t equals usually 0 and have C1 plus C2 equals whatever you're given. And then you'll have to figure out what y prime is. And here it would be for C1 e to the 4t plus, nope, not plus, minus 2 C2 e to the minus 2t. And so you would have, when you plugged in the 0, some other equation to solve there, and two equations to unknowns. You can do something with substitution or something like that, okay? So if it's an initial value problem, it's really just solving a system of equations to do that portion of it. So not all that complicated. Now, with these repeated roots, in this case, you're going to have an equation that looks kind of like this, right? It's going to have y double prime, and it could be plus or minus, and it has to end up with a 2 times something here and then a something squared there, so that when you write down your initial equation, you can see that it's a perfect square. And when you put it back together, you end up with an r minus b quantity squared. So the only solution is r equals b, but it's multiplicity 2. Now, if you had a third order equation, you could hypothetically have multiplicity 3, multiplicity 4 for fourth order. You know, it can be higher for higher order equations. But once you end up with that, what you have is your first solution is going to give you the C1 e to the BT like we did for the distinct solutions. But now for these higher order ones, I'm sorry, for the higher multiplicity parts, then you would build up and you would have a C2T then times the same thing. If it was third order, you'd have one that has a T squared e to the BT, all right? Seems like there's something I should say on that. Yeah, I'm blanking a little bit here. Well, you know that solutions, well, you know that if we take a look at this one here, that we end up getting r equals -1 and it's got a multiplicity of 2. And you know that this solution, since it's got an e to the minus t, is going to go down towards 0 as t goes to infinity. And it's going to do it in a pretty smooth fashion. When you add this extra bit on here, the C2t e to the minus t, those always end up having some kind of a bump, an inflection point, and then going in towards 0 anyhow. So you may have something that's somewhat more complicated in its behavior, but as t goes off to infinity, the exponential is going to be much more powerful in its growth behavior than what the polynomial is. So, all right, real quick. You might have a question here about what on earth motivates somebody to think to put a t times this. You know, we had this thing that was a constant times e to the bt, and then a t times e to the bt, and then if we did a higher order one, it would be maybe t squared e to the bt. The thing that's going on, you can see with this another specific example that I'm just going to say verbally. I didn't think to write this down, sorry. If you have solutions that correspond to having a root of 0, that would be things like a polynomial. So instead of e to the t, you have e to the 0t, which is just 1. And so you would have something like C1 by itself as a solution when that happened. Now, if you think about the equation that generated that, it had to have been y prime equals 0. And then you integrated to figure out what y was equal to. But if you also had y double prime equals 0, you'd have to integrate twice, and you'd end up picking up a t term. If it was y triple prime, you'd have to integrate 3 times, and you pick up a t squared term. The whole thing that's going on is that repeated derivatives are going to end up taking a polynomial and moving it down towards 0. When you have something that's not a root of 0 on these, but some other root, it gets a little bit more complicated. And if you happen to take the differential equations course, hopefully the teacher will talk about the method of annihilators, and that kind of explains why these things work the way they do. But we're kind of just touching the surface. Sorry. So if you have a complex conjugate pair, all right, so when you come down to your solutions, I'm dropping off the A here because we in general will have y double prime as the leading term. And if we go ahead and write out our solution stuff, and I failed to put a piece in here. Hang on, folks, I'm going to edit this on the fly, right? The reason that I'm putting a 2b in there is so that the thing that's appearing down here in this is going to simplify a little bit nicer. So bear with me as I do this. So I'm going to now have the negative, would have been negative b, but now it's negative 2b plus or minus the square root, would have been b squared, but now it's going to be 2b quantity squared, so 4b squared minus 4, a is 1, and c, and then all that divided by 2a. Well, if you notice, there's a factor of 4 that comes out of the square root. When it comes out of the square root, it becomes a 2. And now the 2 cancels because it's a factor of the whole top and the whole bottom, right? So if we are going ahead and thinking about that in the simplest sort of way to look at it, then the stuff under the square root ends up being this b squared minus c. And if you've got a negative number in there because the c was bigger than the b squared, then that makes you have complex solutions. And they always come in conjugate pairs. So like here, you end up getting r squared plus 2r plus 2. And when you get a solution to that, it turns out to be negative 1 plus or minus I. I skipped over doing that. I'm going to trust y'all to go back and look at that yourselves. But then the actual solution may seem like it's out of left field to you. The reason that it looks like this is that we have a super duper famous equation that says e to the I theta equals cosine theta plus I sine theta. So when we had in this portion here an e to the minus 1 plus I times t and a minus 1 minus I times t, you can always do something with linear combinations in order to get rid of the complex parts of it and write it as the e to the real part times t, and then cosine complex part times t, and the same for the sine, all right? We can talk about that in more detail if you'd like, but it's really mostly just a trick of the algebra. So most people just go ahead and, I hate to say it, but memorize that little bit. So, all right, so now we're going to take a look at what to do if you have non-homogeneous terms in your differential equation. We can now, with that, solve all of the second order linear homogeneous differential equations with constant coefficients. That was a mouthful. But now we're going to look at what to do about the non-homogeneous terms. And the method that we're going to talk about is referred to as the method of undetermined coefficients. If what I have to say isn't enough, you might go Google undetermined coefficients, look in the textbook about undetermined coefficients, and also look for the method of superposition. Method of superposition is a big portion of what we're doing right there, okay? So if you have a second order non-homogeneous linear differential equation with constant coefficients, then you're going to be able to find a solution that comes in this form here. The y sub h is just going to be take your equation and make g of t be 0. Just knock out all those things. We refer to that as the associated homogeneous equation. So this is the associated homogeneous solution, and it'll be a general solution with a C1, C2, and stuff like that. And then we need a function, yp, and if you add that general solution to it, then you get the general solution to the non-homogeneous equation. The y sub p is one particular solution. That's why the p appears there. Now, when I say particular, there will be more than one possibility for the answer, but I'm going to give you a method that will always end up in your having the same answer come out. So if we were taking time to learn the variation of parameters technique, that one sometimes comes out with 2 or 3 different possibilities for the y sub p. But what you got to do is to look at your g of t over there. If it does not match any of the terms in y sub h, you're in luck. Because if we got e to the rt, and for some particular r value, you know, maybe it says e to the t, maybe it says e to the minus 2t, but some particular r value. If no term like that appears in the y sub h, then your y sub p is going to take this form of a times e to the rt. And then you just plug that back into the differential equation and solve for a. Because when you plug it back into the equation, you will end up on your left-hand side combining terms together and getting a, or something times a times e to the rt equals, and on the right-hand side, you'll have the something times e to the rt. And so you'll be able to just equate coefficients and solve. Now, if you have multiple pieces, you know, different things that don't look the same, then you need to go ahead and equate the corresponding coefficients. So this can get kind of cumbersome. So let's say my g of t over there doesn't have any exponentials. It's t squared minus 3t. So I made reference earlier to y'all to this notion that those are associated with an indicial equation and getting the solution of r equals 0. So we will think about building up what can happen here with our t squared being the highest degree. So we say a t squared plus bt plus c and solve for the a and the b and the c. Sounds intimidating, but it's just going to be the equating coefficients that we did in Calc 2 in order to solve partial fractions problems. If you didn't solve partial fractions problems in Calc 2, this becomes hard because you have to take a look for that. If you're needing to find more information about that, if you'll Google equating coefficients or partial fractions, you will find some videos out there where people have worked out some examples. So in any case, though, you'll just take the derivatives, plug in, and equate coefficients. So the things that end up being coefficients of t squared get equated on both sides of the equation. The coefficients of t, the coefficients of 1, you just have to sort them out appropriately. Okay. So if you end up with a t e to the rt over there on the right-hand side, then you're going to have to talk about a t e to the rt. And guess what? If it says t squared e to the rt, same deal. Okay. But then finally, there's a little bit of a tricky thing here. Say you've got cosine omega t, just, you know, something like that. The yp needs to go ahead and have a cosine omega t, but also b times sine omega t. So just like the complex conjugates that always come in pairs, if you have these trig functions, the sine and cosine that are showing up, then they have to go together in pairs and you have to solve for both of them. Okay. A lot of times you'll come out to find that maybe this b turns out to be 0 and you didn't need both of them, but there's lots and lots of cases to look at, just lots of cases. So let's take a look at one where we have to follow these kinds of things. So I'm going to get a thinner pen here. All right, so y'all see this, and you know that your associated homogeneous equation would be y double prime minus 3y prime minus 4y equals 0. And your indicial equation would be this, and that factors into this, And so your two solutions are 4 and -1. Okay, so that says that the y sub h that we're going to think about will be the c1 e to the 4t plus c2 e to the minus t. And that's all we have to do with the homogeneous portion. We'll put it together with the non-homogeneous portion in a second. But always do your homogeneous portion first. Please realize that if you are sharp enough that you can go directly from here to here and solve the quadratic equation in your head, I'm totally fine with that. But I have to urge you to make sure that you can actually do that rather than you got like an online calculator to do it for you or something. Okay. So our next bit is going to be figuring out the y sub p, and I guess I need a pen for that. And we look here and see that we've got a 3e to the 2t. E to the 2t does not appear in the y sub h, so that means we can just write a e to the 2t. And of course, yp prime is 2a e to the 2t, and yp double prime is 4a e to the 2t. And that means that my y double prime sub p minus 3 yp prime, sounds ridiculous, 4yp is going to be equal to 4a e to the 2t minus 6a e to the 2t, and then minus 4a e to the 2t, and that needed to be equal to what? 3e to the 2t, right? So I can see that these will simplify to minus 6a e to the 2t equals 3e to the 2t, which tells me that a needs to be -1/2. All right. So now my general solution is -1/2 e to the 2t plus c1 e to the 4t plus c2 e to the minus t. And if I plug in t equals 0, I know that I get -1/2 plus c1 plus c2, and that needs to be equal to 2. I will also need to know that y prime is going to be equal to, let's see, negative e to the 2t and plus 4c1 e to the 4t and minus c2 e to the, I lost my place there, negative t. Yeah. Okay. And when we plug in the 0, we get -1 plus 4c1 minus c2 needs to be equal to what? -1? Okay, I didn't remember that correctly. Oh well. So solving in that, you'd get that your c2 needs to be equal to, oh wait, those -1s cancel, right? Oh, so this is a 4c1. And then if you substitute that back in up here, you can have your c1 plus 4c2. If I add that 1/2 to both sides, then I would have 5/2 over here, and my c2, oh, I said c2, and I meant c1. I hope y'all will pardon that little goof up right there. It's supposed to be a c1. My c1 needs to be equal to 1/2. So my final solution I come to here ends up being y equals -1/2 e to the 2t plus c1 is 1/2 e to the 4t, and then c2 was, what was that? And I'm going to take and scoot that over here a little bit. Plus c2 needed to be 4 times c1, so 2 e to the minus t. All right. So that finally gets me down to my solution here. And yeah, it's a fair amount of work, but each of the pieces is relatively straightforward. You write your initial equation, you get solutions, you write your homogeneous solution, you guess the form of your y sub p, and you plug it in and end up solving for the undetermined coefficient. Then if it's an initial value problem, you've got all that stuff of plugging in the t value and the y value and figuring out what your coefficients need to be. It takes a while, but yeah. All right, so taking a look on this one, we'll do the same thing again. So this has an initial equation, r squared plus 4 equals 0. Got r equals plus or minus 2i. And that says that our y sub h is going to be a, started to do it the wrong way, c1 e to the, oops, nope, that's complex, right? And it doesn't have a real part, so I don't need the e. I'll just go directly to the cosine of 2t plus c2 sine of 2t, okay? So that's your homogeneous portion of the solution. And now we need to figure out what our y sub p is. So taking a look here, we've got 6 sine t. Now that means that the coefficient of the t in there was just 1, not 2. So if we think about what the index was that would have gone with that, that would have been r being plus or minus 1i as opposed to the r being plus or minus 2i. So that means that our our non-homogeneous term and our homogeneous terms don't share a root. So once we know that, we can go ahead and write a cosine t plus b sine t. All right. I always try to use the capital letters when I'm doing the undetermined coefficients part and use the subscripts when I'm doing the homogeneous part. That kind of lets them visually be easier to figure out what's what. All right, so if you're going to plug in for that, you'll have to take the derivatives, and we really need yp double prime. All right, I'm going to skip ahead because this is a derivative that you take often enough that you probably remember that we flip-flop between sine and cosine, and we pick up minus signs on every other term. So that means we end up with that. And so the yp double prime plus 4yp is going to be equal to, and the a cosine t plus b sine t plus 4 times minus a cosine t minus b sine t. And that means that we've really got minus 3a cosine t minus 3b sine t, and that needs to be equal to 6 sine t. That tells me, since there's no cosines on the right-hand side, the a has to be 0. And the b needs to be minus 2. So now we'll write out our y, our final answer here, because it didn't give us initial values. But our y is going to be this minus 2, and see b went with a sign, so minus 2 sine t plus c1 cosine 2t plus c2 sine 2t. Boom. That's all we have to do if it's a general solution. I'm sorry, if it's a differential equation as opposed to being an initial value problem. Initial value problems, there's just a little bit more solving to do. All right. Okay, so now to refer to what happens when we have a shared term, okay? If your g of t contains terms that are in the y sub h, then you're going to have to multiply your form for the g of t by t if it appears once, or t squared if it appears twice. So for instance here, if we had an equation that ended up with a y sub h being having pieces e to the t and e to the minus t, but your g of t was 3 e to the t, then you would have to multiply by t and have a t e to the t in order to get your non-homogeneous part. If, on the other hand, your homogeneous solution had already had the repeated roots coming up there, then your t e to the minus t, you would have to think about the next term up as though there was another repeated root. And this goes to what happens with the method of annihilators that we would talk about if we're going to talk about the theory more. But so your y sub p in that case needs to be just a t squared e to the minus t, all right? If this over here had been t e to the minus t, then we would have had a t cubed e to the minus t. We're always just stepping up however many times we have to because of the roots that appear in the y sub h. All right, let's see. So for this one here, we can see that we're going to get a y sub h. I'm going to cheat a little bit and kind of just move it along, all right? So we'll have a c1 e to the minus t cosine t plus c2 e to the minus 2 or minus t sine t, right? And then when we look over here, we can see that we have an e to the minus t cosine t and an e to the minus t sine t appearing, right? Now, those both correspond to the same root that you would have gotten in here. See, r equals 1 plus or minus I. And they don't have a t or something in them. If one of these had been say a t e to the minus t sine t, then we would have to jump up one more, but we only have to jump up just the one, okay? So we are going to write that our y sub p needs to be a t e to the minus t and cosine t plus b t e to the minus t sine t. Okay. We're probably going to have to add an extra sheet on these. I apologize for that. Oh, and I have forgotten to number them. Thrilling. Okay. So the thing that's going to happen here is that we're going to figure out yp prime, and we have to use the product rule to do it. So e to the minus t cosine t plus t e to the minus t, and that means that we're going to pick up a negative here, and cosine t and plus t e to the minus t. Derivative of cosine is minus sine, so sine t, and then we have to make that minus, and then plus b times, we'll have the e to the minus t sine t, and then minus t e to the minus t sine t, and then the plus t e to the minus t cosine t. This is super messy, folks. I'm sorry. Yp double prime equals, now it's going to get even worse, and we're going to have to try to collect them together in order to make them as painless as possible. actually, you know what? We can save ourselves a little bit of work by tidying up as we go along, right? If I were to spot here that this term and this term go together, and let me get a different color, and these terms go together, then I could write this in a little bit less messy way, even though it may seem like it's not less messy. A e to the minus t cosine t plus b e to the minus t sine t plus quantity minus a plus b t e to the minus t cosine t plus quantity minus a minus b t e to the minus t sine t. Okay, so these are looking pretty messy, right? Let's see what happens with the yp double prime. And so with that, we will have a times, and now we're going to have to use product rule here and here. But when we do the derivative on these, we have already done those derivatives, and we're just going to have to do a kind of a find and replace sort of thing. Earlier, when I said that this was going to be kind of a long presentation, this is what I was talking about. Sorry, minus e to the minus t, cosine t, and then derivative of cosines minus sine, so minus e to the minus t sine t plus b times minus e to the minus t sine t plus derivative of sine is cosine, so e to the minus t cosine t. Okay, so that was not terrible, but now we're going to get to take advantage of what we've done before. So t e to the minus t, when we took its derivative, we put it right here. So I am going to hope that I can copy this out. Copy, paste, put it right here. And I'm going to take my circles and get rid of them. All right. And then I'm going to have plus minus a minus b times the other one. And I don't think I quite grabbed everything. Okay. All right. So that looks like a terrible mess. And what I'm going to do is to add a page and come back across there and do a version of it that's a little bit tidier, because otherwise this is going to take us even longer. So I'm going to look for what my coefficient needs to be for the e to the minus t cosine t. All right. I can see up here, I need to get a minus a. And then here, I will need to get a minus a plus b. And then I missed one. then here I'll need to get just a plus b. So if I tidy those up, that is actually minus 2a plus 2b. So get the messy version out and get the clean version in, and then erase that. Plus, now I'm going to get the stuff that has to do with the e to the minus t sine t. I'm going to see here, I need to get a minus a. And then I can see here, I need to get a minus b. And then here, nope, here is the only place I'm getting a minus a minus b. Okay, so it looks like I really need to have minus 2a minus 2b, right? So let's erase the messy version. Put a cleaner version in its place and have e to the minus t sine t after it. Okay, plus, God. Sorry, folks. The stuff that will go before the t e to the minus t cosine t. All right. So we don't have anything appearing in here or here, but the cosine appears here and here. So that means we need to put a minus a plus b from the first one. Is that right? That is not right. Because we get a minus t e to the minus t cosine t and a minus a plus b, that should be a minus b. And then from the second one, because that's a plus, we'll have a minus a and a minus b. So minus a minus b. So we get rid of the a's and have minus 2b, and I'm going to tidy up and just write that. Okay, and I'm hoping that we get that lucky with the t e to the minus t sine t, right? So we know that those don't appear in the top row, but we have it here. So it's going to get a minus of this. So it'll be a minus b. And then it appears again down here, and it's a minus. So we'll get an a plus b. So plus a plus b, t e to the minus t sine t. Now the a's canceled again. I didn't really expect that. I'm a little bit worried that I might have messed that up. But let me look back and make sure. So that's minus, and yep, and that's minus as well. Okay, looks like it is. So, oh no, I'm sorry, folks. I just did an obvious dumb thing there. That should have been 2a, and I was about to louse it up completely. This is the place where it would be super nice to be doing this live, and y'all could tell me I was wrong instead of my just kind of bumbling along here. All right. So now we're supposed to have yp double prime, I've forgotten it already, plus 2 yp prime plus 2 yp, and see what we end up with. So we are going to have this. Now, I want to cut it. I want to copy it. Right, so that is the yp part. And yeah, then we need to say plus 2 times the yp prime. So I'm going to go back to the previous page, and I am going to copy that. and come back here and paste it, and it got more than I intended. So, but I need to multiply everything in that by 2, right? So I'm going to take and move it up here a little ways. And I'm going to say plus 2 and 2, and a minus 2a, and a plus 2b. And that's just a little bit pressed for space there. And so 2 here, and I have to move that over a little, and 2 there. All right. And then plus 2 times the original, right? So coming back over here, y'all see plus, it was yp double prime plus 2yp prime plus 2yp. So that means that we're going to have to get the original here as well and multiply it by 2. So paste it and put the 2's in it as well. And now we got to see what all we end up with. So first of all, there is a piece of magic that will happen. All right. And you should always be wary when I say magic. We can see that we're supposed to get stuff with no t e to the minus t cosine or t e to the minus t sine. So the thing that's going to happen is going to be that the coefficients of these things are going to combine together somehow magically and get 0. I'm going to go ahead and work it out here, but if you haven't made an arithmetic mistake, maybe an algebra mistake somewhere, this should always happen. So let's go ahead and get the, what the hell was I doing? The t e to the minus t cosine t coefficients, right? So we can see that we have minus 2b here, and yeah, I'm gonna just write it down, minus 2b, and then we will have minus 2a plus 2b, minus 2a plus 2b, and then on the last part here, we will have plus 2a, t e to the minus t cosine t, plus, now when we do the sign, we'll have 2a and minus 2a and minus 2b and plus 2b, t e to the minus t sine t, okay? So those completely cancel out and you don't need them. It will happen every time as long as you did your algebra right. So the only reason to actually do this is to check your algebra. Make sure you haven't dropped any minus signs anywhere. All right, so then plus, now the part that has the e to the minus t cosine t by itself with no t's on it, that probably won't all cancel out. So minus 2a plus 2b, and then where's the next place that appears? Plus 2a, and then plus another 2a, okay? And that is not t, but e to the minus t cosine t. And plus, now the stuff with the e. That wasn't right. That wasn't right, folks. I'm sorry. I just spotted what I did as I was saying it. Let me go back and fix it. Coefficients of just e to the minus t cosine t minus 2a plus 2b. That was here. and then plus 2a here, and there's nothing else. E to the minus t cosine t, all right, plus, and now the coefficients for the sine, minus 2a minus 2b, and then where else does that appear? Here, plus 2b, e to the minus t sine t, and the b's cancel. All right, I have run out of room, but we're going to go ahead and write down here that this is supposed to be equal to what? E to the minus t cosine t minus e to the minus t sine t. All right, I'm going to go ahead and put that onto my next page here. And just write down the simplification so that you can look back at it later and see that we have 2b e to the minus t cosine t, and then minus 2a e to the minus t sine t, and that needs to be equal to e to the minus t cosine t minus e to the minus t sine t. So think of the coefficients there being 1 and minus 1, and you equate the corresponding coefficients, and you find out that a and b are relatively simple to do. B has to be 1/2, and a has to be 1/2 as well. So our final solution that we end up with is 1/2 e to the minus t. I think a went with cos. Oh, it doesn't matter because they're the same thing. T sine t. Okay. And then plus c1. I got to look back to see it. E to the minus t cosine t. Okay. I did not write my t's down here, folks. Sorry. E to the t cosine t plus c2 e to the minus t sine t. Okay. That was a big muddled mess just because there was so much to actually do there. And I realize that is the main big downfall with these, is that you can goof things up by just dropping a minus sign somewhere in the middle, and it'll take forever to find it. So, all right, is this, I think this might be the last, yeah, that was the last one. Oh my goodness. So it is, of course, always good to end on a high note, but my singing voice is terrible, so I won't bother you with that particular joke. Okay. All right. So doing these in class, the main thing that will be kind of a hassle that's different from what I did right there is going to be like at the end when you had two terms. If they ended up being from totally different roots, you could just work one equation at a time. You would not have to work all this stuff all at once. It may feel like it's extra writing, but it'll actually be a little bit shorter. So you can do this. It's fussy and pedantic, but it's totally doable. All right. I'll see you all in class.